is now recording, and I'm going to open up the whiteboard. All right, so let's think about the perceptron here. Oops. So the perceptron. Okay. Basically the idea is that you have input features, right? So you have some input features. Right, so it's just like we've done before. So, you can think of the iris data set, for instance, iris, Fisher's iris, right? And we had, data. Or we can think of MNIST. All right, so 784, et cetera. So we're going to think in terms of vectors like that as input. So then it turns out we can have a little diagram that kind of will look like this idea of neurons in a brain. So if you think about it, we calculate, let's say, a neuron just as a 1, and then these x's are coming from the data, so x1, x2, x3. Dot, dot, dot. Let's generalize to xm. Okay, and so we have these are the inputs, the vector. This is going to be then multiplied by the weights, right? So we're going to learn these weights, this combination, and then this just tells us how important something is. Okay, so this just tells us how important something is. So we can do W3. WM, okay? And then all of these are going to be added in some way, right? And so we're going to say there's, a type of a sum here. Type of a sum, okay? And so all of them combined together. So if you look, it kind of looks like a neuron a little bit, right? And then usually after that, all of this is sort of what is called a linear sum of things. But then you have to make, this gives you one value, right? So this results in a value, and then this value, you have to run it to something, through something. And then, so this is usually called a threshold function. All right, so the threshold function, and that's going to be, something that decides what to do with that data, right? So we're gonna think about, so for instance, some functions out there, like something like the sigmoid, etc. But don't worry about that. So it's just some kind of a function that it takes a value. So if you remember, probably like sines and cosines, right? So you remember those, and you get an angle or something, and then it gives you a value, right? So they're just functions that transform a value or the natural logarithm, things like that. So that's basically what that means, but we can craft that function however we want, okay? So that's also the point. And then once we get this threshold with value, we get an output, right? But just like I said before in the beginning of this week, these weights can initially be picked randomly. So then your values are not going to be very good. Okay, so your values are not very good. Okay, your values are not very good, and so you get this information and you send it back as feedback. So what would be called like the error. Okay, the error, and then here then you do the update. So this is called the weight update. Okay, so the weights update. Okay, And so this is kind of the algorithm that we're going to look. This is called a perceptron. As I said to you guys, you know, it kind of looks like a, you know, you could say it looks like a neuron, basically. So the perceptron, so now some information about what this means. So if you think about it, this little diagram can also be written in a different way, right? So it can be written as a sum, right, of x, a sum of x times w, okay? And then you have, if you look over here, you know, you have an index that goes from 1 to m, right? So you got an I that goes 1 to m, and then these are I, right? And then that's basically the same thing. If you notice, that sort of gives you this value over here. So this value is what you get. And so that would be, you know, and it's all linear, there's nothing else. So let's just say this gives you, you know, a C score or a C value. And then this other part, oops, this other part here, once you get this score, it runs through a function, right? So it runs through a function, okay? And so that just means that now C goes through a function, right? And it gives you, you know, the predicted value Y, okay? So that's really the idea with this perceptron, okay? Now the perceptron is a binary classifier. So it's a binary classifier, okay? Now, this can be written out also if you want to just more intuitively think about it. It's going to be x1. So let me switch back. So this can be written out as just, you know, take a value x1, multiply it times w1 plus x2, w2, and then dot, dot, dot. And you've seen me do this before, right? You've seen me, and as it turns out, this is a common function that we do in machine learning, right? So we have this approach. So this is kind of one of the building blocks, okay? Now there are efficient ways of doing this, okay? So it turns out that we want this formula, right? We want this formula. And really, if you think about it, you can see this perceptron made up of x's and w's, and you can actually write these down as what is called a vector. Okay, so we can write this down as a vector, and we can just use techniques from linear algebra to make the computation really effective. So I can take this and just say, you know what, I'm going to take x, a generalized x, you know, call it vector, and a generalized w, call it vector. And then now I'm going to have in there x1, x2, x3, dot, 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 xm. And I'm also going to have in here w1, w2, w3, dot, 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 wm. Okay, so you end up with the two vectors, and now we want to end up with this, right? We want to end up with this. This sum gives us basically our C value, which is the thing that we want. And so it turns out that there's something in linear algebra called the dot product. So it's just a technique. That's all it is. Just very much like you would have a function that you write, you know, you write your function for something. This is called a dot product, and it's a very important operation, very highly efficient operation. It's a method. It's a method of multiplying two vectors. Okay, which, by the way, you know, those two are vectors, right? And so we can just say now, since we have x and w, all we have to do is take x, dot product, that little dot like that, w vector, right? And as it turns out, the definition of the multiplication in a linear algebra space with two vectors like this turns out to be I equal 1 m of x I times w I. So if you notice, this one is exactly the same as that one, okay? And so, and we can use basically that function that converts this into x1 w1 plus x2 w2 plus dot 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 xm wm, okay? And so that takes care of our, makes this computation really efficient. Now we did something pretty similar when we calculated the Euclidean distance, right? So if you remember at the very beginning of the semester, we also did this for the Euclidean distance. All right, so now how do we implement this in code? If we wanted to write this in code, we could. Now all semester we've been using Numpy, right? So as you might imagine, Numpy has a built-in function that will do that operation for us. But if you want to, sometimes Numpy is not like the type of coding that we're used to, a little bit more sequential. So if you want to get even more of an intuition about it, we can write the code. So I'm just going to say dot product operation in Python. Let's define a function. So we can call it the dot product function. As you can see here, it would take two NumPy arrays. So these are, two NumPy arrays, pretty much in the definition that we've been seeing all semester. And then you have return. And then now notice that we're going to use a list comprehension basically, right? And we do, so what do we need? We have the vectors, so we just need a for loop. So for I in range. And then what do we need? We need the length of one of the vectors. So let's say A. They both have the same length, therefore we only need the length of one, and we have the length of both. And then once we do this list comprehension, then here we can just use that index to take A, that element I, times B, that element I. Oops, that should be a square bracket. And so we make the multiplication there, and then finally, once this is going to our list comprehension, remember, returns a list of the multiplication. So it basically would give us a list of this one. It's going to put all of these in a list, and now all we have to do is add them up. So I'm going to do a sum. Okay, and that's basically it. So that that's as simple as that to implement the dot product, which will be one of the tools that we're going to try to implement today. Okay, so that is the idea here with the Perceptron. So that's some of the intuition that we can use. All right, so now that we have this idea, right? So as you know, we're talking about neural nets. We're talking about neural nets, and so this is the function that we're going to try to implement and then run it through some of our code. So let's go ahead now and switch over to our Jupyter notebook, and let's just try to implement this from scratch, right? So let's go. Stop sharing here, and now I'm going to do Jupyter. Okay, so we have, let's just go to the folder here. And I'm going to share this screen. Okay. All right, so let's create a new, so let's actually, since there's so many things in this folder, let me actually just create a new folder in there. right, so I'm going to go. All right, so in here, I'm going to create a new file. All right, there we go. All right, so now we, we're going to use Numpy here. Okay, so we're going to use Numpy. So import Numpy as NP. Okay, so we have that. And then we can start thinking about building this, right? So we're going to need some parameters. We're going to need a couple of functions. So we need, now the operation that I just showed you, we're just going to use the built-in function from Numpy. So we need, let's see, we need at least two functions, right? We need a fit function, fit, right? And, we're just going to say something here. And then we're going to need also predict. Okay, but very similar to what we've done before in all of our other examples. Okay, so we have that. Now we are going to, let's start with the predict, which is probably the easiest one. So first we're going to say the linear output will be equal to NP dot. And this is the dot product that I just described. And then that, of course, takes, let's say X, where X would be the value that we are passing. Remember, this could be a matrix of values. And then we have the weights. And the weights are the thing that we are going to learn. Plus, there's always this idea of another term that you should add called a bias. Okay? So we have this. Now, what part of what I just showed is this? So if we go back to the share screen, if we go back here, that basically is this, right? So that basically is this. So if we go to the diagram, basically there, I'm taking the X vector or X data, the weights, and I'm performing this dot product, which results in this. So that variable linear output is this thing here. Okay, so this is linear output. So if we think about it, then, we are doing this calculation, but we're doing it in this way as, a method of multiplying two vectors as a dot product. And it's basically this function dot product, only we're doing it in NumPy instead of doing it, kind of like in regular Python with a list. Instead of a list, basically, we're using a NumPy array. The next part will be that, so if we go back, now we have until here, but we need to take this value and pass it through this other function and modify it, right? So that's the next part that we're gonna take a look at. So now let's take this, this is now activation function. Right, that's the activation function. And then we have linear output. Okay, so the linear output goes through this function, and then it produces ypred, okay, which is then, or y predicted, however you want to call it, and then that's what you predict, ypred. Okay, so one of the things we need to do then is we need to define that function. Okay, so that's the next thing that we need to do is define that function. So we called it activation function. And, you know, we can just call it activation function. Right? And as you can see then, here we need to have some logic about what we're going to do. So usually this activation function can get pretty complex, and there's a lot of things that you could write in here. So for now, you know, the easiest thing that we could say is, because we want to use this to predict classes, is given the value, we're going to return some logic basically. So we can use the that value and basically say if this, oh, I don't have the value. So activation function takes a linear input, right? Let's call this one little x. So if x is greater than or equal to 0, right, then return 1. Else return 0. Okay, and that's basically the approach. So you can see very straightforwardly, that's it. You know, that's all it is. We have, you know, if we go back to our diagram, we can see that the perceptron is pretty straightforward. We just take our data, iris or mness, right? And then we already have this W weights vector because we already trained. We run this through, it gives us a linear by the dot product, then we run it through some function, and then we get an output. Boom, done. You just did your first neural network. You see that? So feel, you know, very simple. Well, let's say a neural network from the late 1940s, but still. So it's only 80 years old, but still, it is, you know, in essence, a neural net that back then was implemented in almost in like hardware. So what's the problem though? What are we missing? Well, we're missing these weights, right? So we don't have that. And this, you saw me, I added that term bias. So that bias, you can think of it as just, if all of these are X's, then this is a 1 and it's associated with that W. Okay, so that, you know, we can think of a bias term like that. It's just an additional parameter that you add to the function that it'll learn. Because sometimes lines in a vector space, you know, get moved a little by the bias. So, and it moves the entire line together. So now the trick is then we need to learn these W's, right? And that's what I want you to understand. That's why Perceptron is so important, because it shows you that's what neural nets do, okay? You give it this value, you give it some random weights, it predicts this through a function, then you get here to the final predicted output, you compare it to the real one. Remember that you compare it to the real one, and then you feed back the error back into the network to update the W's, okay? And so today, you know, that's what we're doing with the Perceptron, but in a very simple way. So now we need to focus then on this W's vector, okay? So we're gonna go then back to the Jupyter, and here then now, okay, so now we need to go back to the fit function. So as you might imagine, the fit function is the function that helps you to calculate the weights. Because if you notice, the X is just the data, right, that we're trying to predict. But the weights and the bias, these two parameters, we need to pass and we need to calculate beforehand. All right, and that's what we're gonna focus on then in the we're going to focus then on the fit function. So in the fit function, we need other data, what is called the training data. Remember how we divide our data into X train and X test, right? Do you guys remember that? So this is technically X test, okay? And then we're gonna get its predicted data. So this data here then should be X train. But we also need the labels, right? So we also need the labels. So we're gonna need Y train as well, okay? So with these parameters now, we're gonna go ahead and figure out how can we learn the weights. So we're not gonna use gradient descent or back propagation or anything like that in this example, right? The perceptron is pretty straightforward in that sense. So we're just gonna kind of do it from scratch here in a very simple way. All right, we're gonna try to figure this out, okay? So the first thing that we wanna know is, given the data, we wanna know the number of samples and features. All right, so if you think of iris, how many samples? Well, if you take iris and you divide it into 100 samples for training, 50 for testing, then 100 samples should be, you know, the number of samples, and then the columns is 4, right? So we're gonna create these variables, n samples and n features. All right, and so now all right, so now we have the fit process. Okay, we also need now to have these variables, right? So we need to calculate, as I said, the weights. We need to calculate the weights, and we need to calculate the bias. All right, so we have here, for instance, np dot zeros, right? And why is it np zeros? We're just going to create, we've done this before also, and we saw this in some of the examples. We're creating a vector of all zeros of size. What should be the size of this? Well, think about it. We're going to multiply, right, the x times the w. So the data times the weights. So the size of it is m, right? The same size. So the same size of the weights should be the same size of the x's, because this we're going to treat as a separate term called the bias. So we really just focus on this part here. And so to get the size of w, we just need the size of x because they have this. So that's it. So we go then, we go here, right? And np zeros will be n features. So if we're talking about iris, remember iris has 4 features, which are sepal width, sepal height, and then something else. So they got 4, I think. Is iris 4? Or is it 6? 4, right? Yeah, I think it's 4. Yeah, thank you. All right, so that's it. So we created a vector of all zeros. So think of it as, you know, think of it as like that, right? So, and that's all it is. We're creating that vector. And so we're now you could initialize this randomly. So you assume like a normal distribution of centered around 0 or something, and then you plug in random numbers. Sometimes it's better to have random numbers than all zeros. However, all zeros is fine here. It's not going to be a problem. Okay, so now the bias is just going to be the additional term that, so we're going to, if you think about it, is 1 times whatever this is. So really, we can just say bias here, and let's just initialize it to 0 as well. All right, and so now we then want to figure out what to do here. So now the y's should be, of course, our trained data, okay? And the x's should be our samples, okay? So now let's go and just take a look at what we would do. So intuitively, just like we do with a lot of things in machine learning, you're going to have some kind of a for loop. So let's say for, now whenever you do this in Python, a little underscore, it just means that you're grabbing the object, but you're not going to use it. So it's really just it helps you to do an iteration. So for, you know, underscore in range, okay, and then we do number of iterations, okay? So number of iterations is how many times we're gonna do this. So let's say, you know, 200. You can create a variable and play with it, but you know, let's just hard code it. Why not? Then, so you repeat, now this is important, okay? This is very important. In deep learning, which is the direction that we're going into, neural nets, it's actually, as it turns out, whenever you have a training set, let's say like Iris, which has 100 samples for training, or you have MNIST, where you have 60,000 samples for training, you basically train the model with the 60,000 samples, not just once, but several times. So in this case, for instance, I'm saying train the model 200 times with the same data set. So what that means is feed it 60,000, right? Train it, then start again. Feed it 60,000 again. Train it more. Again, the same, and it's the same 60,000, by the way. So 60,000, the same 60,000, 200 times. And that's really, it's basically a standard approach. You know, it's funny that this took me a long time, I remember, to understand this issue. Why, you know, that it just works better. But sometimes nobody says anything about the number of iterations. And that's really what it means, is that you're going to train your data, you know, with the same data 200 times. Okay. So hopefully that makes sense. So now that we're going to do that, then we have another for loop. This for loop is if the top one is about just repeating the same task 200 times, this new one is about reading the data, right, once. So we're going to use the enumerate, so that's very convenient. I think we've used it also this semester. Xi, let's say. So we're going to enumerate. So we're going to enumerate through our data, X. So the advantage of using enumerate, it's very convenient because what it does is, think about this, right? So you have for IDX, Xi in enumerate X. So let's go to the whiteboard and think about that one a little bit. All right, so if you think about it a little bit, X is like this. All right, and let's say it's MNIST, so it's 60,000. So then, and then this is 784. What that enumerate is doing is grabbing the first one, right? And so that's why it's called Xi, because it's, you know, this X, if this is uppercase X, it's a little X, it grabs the whole row. So in the enumerate and it grabs the index. So first iteration, we grab 1 and Xi, where Xi is the whole row. Next iteration, IDX, so this is IDX. IDX is 2, it grabs this one, Xi. You see that? Number 3, Xi, IDX, right, and so on, right? So dot, dot, dot. So we're doing this enumerate. That way we have an index for every row, plus we have the entire vector. So now we have vectors of 1 by 784, excuse me, 1 by 784 every time. Guess what? We have the X's. Why is that convenient? Because, you know, like this, right? We need the X and the W's. So we're grabbing Xi is basically this one, right? We're grabbing it now, the train data. And then we already have this one, which is a whole bunch of zeros so far, right? But that's what we need to learn. We need to learn this one. So the intuition of this is, you know, if you think about it, whenever you guys make decisions, right? You know, let's say that you're going to go ride your bicycle or your bike or your motorcycle, whatever. You know, you know, what do you look at? What's the one variable that's extremely important that you give a lot of importance to before you go ride your bike? What would that be?
Before you ride the bike?
Decide to go out and grab your bike and start it out and everything, what would you, what's the one variable that you look at?
Oh, well, I guess you got to look at the weather, the tires.
Weather, right? Yeah, that, you know, if it's really windy, if it's raining, or if it's ice on the roads, things like that. So how much do you, let's say you get the variable of ice on the road. You multiply that times a W. There's a W in your brain that you learned. A long time ago when you were a baby, that W was a 0. You had no clue. It could be icy. You'd get on your bike and you know, your little bike, and then you'd have you'd fall, right? So you learn over time, you know what? Whenever I see ice, I'm going to multiply it times a W. And that W now is what? It's almost 1, correct? It's a real, or even higher. It's a really high value that says, you know what? If it's raining or if it's icy, I'm not going out. However, you might see another variable where you see a squirrel in the grass. What weight do you give that squirrel in the grass in relation to riding your bike?
A pretty low weight.
Low weight, right? It's unimportant. That's the whole point of this, right? So that's what we're trying to do. We need to learn these weights based on the x's. So the squirrel, rain, you know, icy condition, that's the x. The zeros, we don't know yet. You're a baby. But over time, as you see examples, you'll know which ones are important, which ones aren't. And that's exactly what we're trying to do. So now we go back to our Perceptron algorithm. All right, and now we know, okay, we've got the x's here. We got the for loop. All right, and what else do we need to do? So now we're in the loop here. And what do we need to do? We need to, in the training, we do the exact same thing we do in the predict. So basically, we can just we literally do this again, right? But this time we do it for training. So I'm going to say linear. If you look, it's pretty much what I have down there. Linear output is going to be equal to NP dot, okay? Linear output NP dot, right? And what do we do here? It's basically XI, and now we multiply times the weights. Keep in mind though, our weights are currently all zeros. So it's gonna be pretty bad, right? It's gonna, you know, basically multiplication times 0, what does that give you? Uh-oh, you know, that's trouble, right? And so we gotta think a little bit about that. That's why randomizing this data is better, right? Randomizing it is better. But let's just think about the logic for now. And we add this bias term, right? Which kind of signifies, as I said, this other parameter over here, this one. You see me circling over it. So now, but let's keep going, right? So we're gonna do this multiplication, linear output. Now we have y pred. I just like to do this for alignment. So y pred is what we're going to predict. What do we use? We use our activation function over here. So the activation function, just like I described before, just takes the values and it's going to perform something. So this is linear output, like that, right? So we have those parameters. Now the question is, we need to have an update rule, right? So here, this in neural nets, this is where we would, you know, compare predicted with real value, because we have real values. What are the real values? The real values are the ones in Y train, right? but we give it this from this X train. Oh, and by the way, this should be X train. So X train, right? We have the values. We take the weights that are 0. You're a baby. You predict linear output, then activation function, Y pred. This Y pred now should be compared with something from Y train, right? The corresponding value from Y train, right? So compare predicted with real. So it's almost like somebody's telling you, hey, I want you to learn how to play, play tennis, right? So play tennis, and so they show you, okay, so they say, all right, this is how I do it, and this is, an instructor, so they're really good. They show you the right swing, they hit the ball just in a certain way, then you do it, and you do it really bad, right? And so you compare what you did with what the instructor did, and you somehow find, okay, I need to do it more like you in this way. I'm going to adjust my arm, my swing, my angle, all these kinds of things, right? So that's really what we're doing here. You compare the predicted with real value. And this is done throughout machine learning, right? Or neural nets. However, the way that I'm going to do this is now only specific to the perceptron. So perceptron update rule. Okay, so the perceptron update rule is going to be the update that we're going to do here. Okay. All right, so now in the perceptron update rule, if you notice, let's just create a variable update where we compare the Y pred, right, the value that we just got, Y pred, minus the value that's the real. Where's the real? The real is in Y train, right? That's a value, let's say in iris, is it setosa, virginica, or versicolor, right? But remember, this is binary. So this is actually only assuming classes that are binary, and the classes for 2 class only, let's say. For 2 class only, back in the 40s, they weren't so concerned with 3 classes, right? They could barely get 2 classes to go. And so, this one only really does it because it's a lot easier. If you do it multi-class, it just becomes a little bit harder. But it's not impossible, actually. It's not impossible at all. You could build multiple of these, which is called one versus all. So it's like, if you have 3 classes, you could just say, is it class 1 or another? Is it class 2 or another? Is it class 3 or another? And you can start playing with that in some way. So now we need to take the value from Y train, right? So we have Y train. Now this is where the IDX becomes really handy, because we know, if you remember, if I go back to the whiteboard, go back to the whiteboard now. Go back to the whiteboard. Y. You see, we grab the corresponding label. 1, 2, 3, 60,000, right? We have the labels. IDX.1 will correspond to the given vector and its associated class. So that's why the enumerate was really, really handy. Okay. All right, so let's go over here then. All right, so now we have so what do we need to do? We need to put in the IDX in there. By putting the IDX, we know that we have now the corresponding real value. Does this make sense, guys, that we're comparing the real value to the predicted? Any questions there?
Yeah, that makes sense.
All right, great. And now the question that we're going to have is, if you think about it, this is a value, right? So this is going to be a value. Let's say it's, you know, just to think, you know, 1 minus 3 for whatever reason, and that's 2. Now, keep in mind that this value 2 could possibly be added to the weights, right? To you know, add this or subtract. However, that's a big increment sometimes, right? So the increment can be really big or really small. And we can actually control that by multiplying this times a value that we're going to call the learning rate. And as it turns out, the learning rate is also extremely important in machine learning. So you do this in the Perceptron. Imagine this was invented in the 40s and you still do it today. So if we go back to this, you can see here what the learning rate means is if you're calculating the weights, right, to try to arrive at that optimal solution, right? Let's say that the optimal solution is down here. If you in your weight value, remember we had drawn this chart before. Your weight value was here. You're here at I, and it's not optimal, right? What you're gonna do is you're gonna update that W, you know, you say update, right? So you add that value to it. However, if this value is too big, what's gonna happen? It's gonna increment quite a lot. Now, what if it's too big? You could end up here, where you actually, you know, pass this. So you take what is called a too big of a step, right? So it's preferable to just make this a little bit smaller by multiplying this times that learning rate. The learning rate is usually a very tiny value, like 0.001. So it just has the effect that now it makes the increments that you have very tiny. So now you can see it just adds that little piece, right? And now you jump there, right? And you jump, and then the next time you add a little piece and you jump there. You see that? And so now what if you make this too tiny? Well, if you make this too tiny, I mean, it could be infinitely tiny, right? And you don't want that either, because if you make it infinitely tiny, it's going to take forever. Imagine if it's just like, it takes a million iterations, you know, it's going to take forever, right? So you could make it, you know, almost infinity, you know, you know, it's going to take forever. It's basically 0. You're going to have a nan, not a number error, and all kinds of things like that. So this is the idea, right? So how much do you update the W's by? If you make it too tiny, it'll take forever. If you make it too big, you're actually going to skip things where it just, you know, jumps, let's say like that, and you never arrive at an optimal solution. So the learning rate is kind of trial and error, but usually you can't go wrong, honestly. Or let me put it this way. Usually the default value for that is something like 0.001. So let's just try that. Okay, so we're going to say learning rate equals 0.001, something like that. And then now we multiply it so that we know how much to update by. Right, so we know how much to update by. So now this, of course, assumes that your values, that you just have a 2-class problem, okay? That you just have a 2-class problem. So we may need to do something to the y. So let's actually, instead of calling it y train, let's do just y like that, y underscore. And before then, we're going to modify the y's. So we're going to create a list, right, like this. And this will give us an opportunity to modify the labels if we need to. So NumPy, let's create a NumPy array, right? A NumPy array, and then we're going to use the list comprehension here. And all I'm going to do, you'll see, is I'm going to iterate through this. So I'm going to say for, let's say, I in Y train. So now I'm going to grab the labels from Y train, and I could modify them if I want to, from whatever the values are to other values. But for now, I'm just going to keep it as that. So I'm just going to say, so I basically just did the same, right? So the same I had in there is the same I have now, but this gives us the option of coming back to this and modifying the values, okay? So that way then, you know, if we need, if somehow the machine learning algorithm is not working very well because the values are -1 and 1, we can change it to 0, 1, 2, or 0, 1, or if it's 0, 1 and we want to change it to -1 plus 1. It's just, you know, something we can do, a little trick. So now that we have the update rule, all we want to do is we want to update the weights, right? We want to update the weights. So we have YPRED, right? And now based on that difference, remember, this is going to be a difference, right? So in essence, what would happen if we predict the same thing that we had? So if YPRED and real are the same, what happens? They're the same number, right? So 1 minus 1, 0. Or 0 minus 0, 0. Or -1 minus -1. What is that? 0, right? So it's always going to give us a 0. So basically, then that's a 0. This times a 0 is a 0. So the update doesn't do anything. Okay. However, if there's a difference, the weights will be changed. And so that's what we're going to do now. We're going to look at the weights, the vector of weights, right? And we're going to say weights. We're going to modify the entire weights based on the update rule. So we're going to say plus update. Okay, update. And we're going to multiply the update also with the x. Okay, that's just a kind of a, this sort of, you know, you can always do like the derivation and it comes out to this, but let's just kind of, so we don't have to complicate it, let's just kind of accept it that we also look at the x data as well, xi. And that way we end up adding a vector plus a vector, right? So if you think about it, this is going to be the weights vector, which is, you know, initially 0. Only at the beginning is it 0, right? Then we add this, we add to it the x vector, okay? So this is x1, x2, x3, x4, you know, dot, dot, dot. And we multiply every value in x by the value of update, which is a tiny value. But one thing that is extremely important about this is the sign. Is it positive or negative? So this value, the update can sometimes be positive, sometimes be negative, which means that sometimes you're going to be subtracting from the weights, sometimes you're going to be adding to the weights. And that's really like the essential thing. Do you decrease that particular weight? Do you, you know, or not? Right? And so obviously in the future, or you might imagine other neural nets will be a lot more advanced than this, okay? But this, you know, gives us a good intuition, and as it turns out, neural nets are still very much like this, only the way that you do this part, you still do it, but the way that you do it changes, okay? And that's why we, in a sense, that's why we end up with so many different neural networks, because of that little piece of it that changes. All right, we also do the same for the bias. So the bias vector is going to be equal to bias plus the update. So we're just going to update it. All right, you see that there. And that's it. That's literally all that happens here. You do this in the training. And then fit should return what we're going to need, the data from fit, right? So fit should then return. So when we do this, when we do like the training, you know, we're going to have, so if we do it down here, we're going to have our X data. So we read our X train. So get this from, we get this from somewhere, right? So get data, let's say. Then Y train, right? And then, get data. And then once we have that, we're going to call fit, right? So our function is called fit here. So we can just say fit. And what do we need to fit it? We need X train and Y train. So we fit these values in here, X train, Y train. And then what should this return? Well, what does the train return? Let's think about it. What else do we need? When we do the predict, oh, here in predict, I think I forgot the return. All right, so predict gives us Y pred, right? So it gives us Y pred. And so that basically means we take predict, and predict takes X train, oh no, it takes X test, right? X test, right? And yeah, that's basically all it does. It takes X test, and then that gives us Y pred, and we're done. Then we would probably use like the accuracy function that we had created before, right? And I'm just going to say here, compare Y pred to Y test. So we're going to also need Y test. So we need those as well, right? So we're going to say X test get data and Y, oops, ooh, I ran this by accident, sorry. Maybe it's a good time to save it, huh? Did I not even give this a name? No, I did not. All right, so let me, this is called a Perceptron. Should have done this. Perceptron. Okay. And I'm going to also save it and overwrite it. Save, and now just to make sure, I'm going to open Perceptron, and there we go. All right, so as you can see, I also need Y test. We get the data. This is exactly what we've done. KNN, naive Bayes, all the other ones. And so now you would compare them, and that's it. You could also print your results. So you're going to do print Y pred. Do you see that, guys? That's basically it. Oh, here where I was going with this is that what do you need in predict? So predict needs, oh, sorry, not predict. Well, actually predict, yeah. Predict needs the weights. You see that? It needs the weights and the bias. It's got the X test. Then everything else, this activation function doesn't need anything. Therefore, we need to pass to this the weights and the bias. Right? So we're going to pass weights and bias. Weights and bias, which means that the fit function now, what does the fit function return? If you think about it, we give it X train and Y train, and then it calculates weights and bias. It trains, it does the app update, and it updates weights and bias. So it should return weights and bias, right? That's the learn part. So again, going back to the example of riding your bike, you're going to give it a lot of examples of riding your bike. The variables are raining, icy roads, wind, and also squirrel in the grass. So of those, probably if you're riding a motorcycle, the most important one is icy roads. You don't want to kill yourself, right? The least important is squirrel in the grass. However, if you're riding your bicycle, I don't think you're going to be on the interstate, so maybe icy roads are not as important anymore, as much as, you know, wind is okay, like it's going to give you a better workout because you're riding against the wind. But really, the one that's the most important is getting wet, right? You don't want to get wet. Getting wet also would be important for riding a motorcycle. So in any case, the whole point is you learn those weights by doing this. And now all you have to do is return weights and bias. Okay? So that's it. You know, so then the fit function gives you the weights, comma bias. And now you have built your first neural network. Does this make sense, guys? Are there any questions so far?
No questions here.
Pretty clear? All right, so now that we have this code, let's go ahead and let's try to, I believe everything is there, right? I believe everything is there now in the logic of the algorithm. Now what we want to do is we want to test this out. We want to test this out by giving it some data, right? So we're going to now look at giving it some data and, you know, try to work out if there's any problems. All right, we're going to need, of course, a few functions, like we're going to need our accuracy. So first of all, let's come up with some data. So this is kind of, you know, let's now not do this, right? And let's actually have real data. All right, so we're going to take X, we're going to create some fake data, right? So some fake data. You guys can, now my suggestion is, you know, I'm not going to assign a homework for the Perceptron, but I recommend, though, run this with Iris and MNIST. You know, convince yourself. This is just like the other ones. I've given you an algorithm just like naive Bayes and the other ones. In here, actually, the only problem, though, sorry, is that it's a two-class problem. So actually, I think one of the data sets I gave you is binary, or I'll give you a data set that's binary because it won't run for multi-class. Just give me a sec. Let me get some. All right, so let's create some fake data. We're going to need some libraries for that, if you remember. You know, it's always just, we want to see that it works. So sklearn. Sklearn, I believe, have we used sklearn before, guys? Remind me.
Yeah, a couple times.
So that's it. So we've already installed it. If not, if you have, it's pip install. You have to go to the Anaconda prompt and then pip install sklearn. But all right, so we have it. So from sklearn dot model selection. So if you take ITS 520, the grad level class, then that class is a little bit more applied, less on the fundamentals because you've hopefully taken 365 already. So that one is a lot more sklearn. All right, so and TensorFlow. So model selection is over here, right? So from sklearn model selection, import, and we want to import train and test so that we can do the split easily. So we can also do that with Numpy, but this is just, you know, easier. One line of code does it. So, all right. So from sklearn model selection, import train test split. So that's just to make our lives easier. Also from sklearn, let's let's import data sets. Okay. So we can import data sets, and hopefully that'll do it. So now let's create some random data, X and Y. Let's go over here. create our data. So data sets, right, dot make blobs. So make blob, I think we used this also before. So make blobs, and we're just going to create some data here. Let's say we're going to create n samples, where n samples can be equal to, let's say, 150. So if you notice, it looks a little bit like iris. N features, this could be any kind of number of features. Let's just do 2, but I suggest you guys try with 4, with 10, play around with that. And then the data is going to follow a distribution. So we're going to say, we're going to give it some parameters here. So we're going to say centers equal 2, right? So 2 classes basically. And cluster data should have a standard deviation. So it's going to be centered usually around 0, I think, and then a standard deviation of 1.05. So don't worry about this. This is just to create the data. Fake data, you could always just use a data set or create it manually. And then random state, this is just so that we can always replicate the same data set. All right, so now we have hopefully our data, right, X and Y. Now let's go ahead and think about, we need to do the X train, Y train, all that, right? So X train, X test, Y train, Y test. All right, and then train, test, split, and then we just provide X comma Y test size 0.2. So remember what this means is that 80% will be used for training, 20% will be used for testing. And random state again for this split so that we can replicate it. We can give it any value we want. So 1, 2, 3, or so. All right, so now I have both of my data sets created. Let's also go ahead and we will need this one, right? Compare Y-pred to Y-test. So let's just use that accuracy function that we had defined before. So we can do here, I guess. The function, we're going to define it as, define accuracy, right? So we had done this before. So define accuracy. It takes Y true and Y pred. And now we do accuracy np.sum. If you remember, this was just, we've already talked about this, so you can just refer back to the previous video. This was just, we calculate the sum of the equals, right? Because remember, we're going to do a Boolean here where we do Y true equal to Y pred, right? So if you remember, this just says which ones are equal, which ones are not of those 2 vectors. It gives a 0 to the ones that are not equal and a 1 to the ones that are equal. So then when you do the sum, all you have to do is divide by the total number. Y true, like that, right? and then we just return accuracy. And that's basically our function and our data sets, right? So as you can see, we have the accuracy now, so we can use it down here. Now we have ypred, right? We have ypred, and we have basically ytrue is actually ytest, right? So we can then call the function accuracy, which returns a value. So we print accuracy ytrue, comma, ypred. You see that? So that gives us basically our result. Okay? And so now we have our data. We have the accuracy function defined. And what we need now is, now notice I gave it only 200 iterations. Maybe we should do this. These are parameters that you can play with. Maybe try 1,000, etc. So you need to play with those. And then after that, we just do fit, right? So we're going to call the fit function, which actually I think we've already called it. So it's down here, right? So then we do this function fit, okay, with x train, y train, and then we do predict. And so let's actually put these two together here. So we've done that part, right? And now, so now in theory it should work. All right, so now comes the part where everything breaks down. So let's see what happens. Let me save this. Let's go ahead and run it. It'll probably give us an error, I'm assuming. I think it's running because, okay, there's the first error. Let's see. Oh, that's set, so that's probably a typo. Yep. Data sets, all right, so let's try it again. Okay, run it. Another error. Let's see, what is this one about? The truth value of an array with more than one element is ambiguous. Use any, oh, okay, so this X is not liking it. Here, this is what it doesn't like. So let's try, instead of that, so it's in the activation function. So it has to do with it being a NumPy array. So let's try a NumPy way of doing this. Let's do return NumPy dot where. So where is like an if statement. So we're going to say if x greater than or equal to 0, right? Return 1, else return 0, for instance, right? So that's the condition. So basically, remember, if the value is negative, you know, it's going to be less than 0. If the value is positive, it's going to be more than 0. Something else we should probably do is look at the data. So let's take a look at X train here. So we're going to look at X train and what we get, and also the labels, right? So let's take a look at X. So we only have two features, right? So we have, if you remember, we can just slice the data, right? So I'm going to slice the data. This will give us a little bit more intuition. And we're just going to say that we want from just the first 10 rows and all columns. So that's, you know, if you remember, this is how you slice. I'm also going to print the Y, And that is just again, the first 10. Okay, and now we can see what the data looks like. So hopefully that part will print at least. Right, so there's your data. You can see that the data looks like this, the X data. These are the features. That's not such an issue. And then you can see our labels look like this. So this is probably the prediction. But you can see it's predicting some zeros and some ones. This here is what classes we have. 1, 0, 1, 1, 0. So you can see some are ones, some are zeros. Okay? That's like saying some are images of cats, some are images of dogs. Okay? So then we're getting there. Now there's another little typo here. Why true is not defined in accuracy. Okay. What is that? Why pred? Oh, it's because y true is y test, right? That's what it should be, y test, yeah. Okay, y test. All right, so hopefully it'll run this time because that was the last line of code. So now we can run it. Okay. Ah, there we go. What's the accuracy?
0.466.
Very good accuracy, right? Not very good accuracy. All right, so let's take a look at this. We can print, oops, what did I do? We can print y test, again, we can print, so actually I'm gonna take this one out. It's more meaningful to print, you know, let's say y test, this is the correct, the first, let's say 20. Right? And then we're going to do the same with y pred, first 20, and let's compare them. Let's see what, you know, because it's not very good, it seems. There'll be a line. Let me add a print. Okay. All right. So let's go ahead and do this one. Okay. And now we can run. All right. There we go. So it says that it's not very good. And you can see that the top one is the real data. This one is the real data. You can see that for the most part, it has a tendency to think everything is a 1. But some were made zeros, right? Some were made zeros. So our algorithm, there's some issue there with our algorithm that it's not working very well. So our data initially, this is the X data, and I believe we are printing, yeah, so we are printing the data. Now, what is this X and, yeah, X and Y, right? So that's the data. So the labels, the X's doesn't matter really. I think the issue is with the labels. There's 0 and 1. 0 and 1. So that should be fine. I think that should be fine. So the algorithm, so what I'm trying to say is the algorithm is done, right? So you can see the algorithm is predicting. The only problem is it is not predicting very well. So now comes the hard part, right? Now comes the thing of making, this is, and this actually underscores how it is with neural nets. Neural nets now comes the part where you have to figure out why it's not predicting really well, and you have to adjust some things about it. So we are the data I've created, and I think it's correct. I don't see anything wrong with it. There's two classes in there, so there's no issues. Okay. Let me go back to. So it's maybe in the perceptron is the issue. Maybe, maybe. Now we have very few samples here, so let's see. Let's change the learning rate. Maybe it's just not learning because it's too tiny. So that's something to try. Let's do 0, 1. I have, and I'm going to give it more iterations. I'm going to give it 2,000 iterations. All right, let's try it not like that. Just see what happens. Our goal is obviously, we want to get at least to 60%, but higher than that even if we can. It should be an easy enough problem. So nope, that did not work. Still doesn't give us great results. Not learning. So let's iterate through it then. Let's see what happens. I'm curious to see what happens in this equation. This where is iffy to me. So let me just print this. Print X. All right, let's do that. What happens there? All right, so what do you guys see? It predicts these numbers. Look at the numbers there. It's predicting. So all those values are positive. Okay. We get an X. Let me play with this here. This I, let's see, if I greater than 0, else 0, otherwise 1. Okay. Let's try that. Still 46. Okay. So let me. I'm going to take this out because it's taking too much. Well, I don't think giving it more iterations will do it. Yeah, so 46 still. Now we know it's predicting some as zeros and ones, so at least I'd be more concerned if this was all ones. So it's possible I made a mistake somewhere and I just have to recheck all the code again. So I certainly would need to do that. I don't believe that this data set would be so complex that it wouldn't work. Any thoughts, guys? Any ideas? It's running. So the only thing I can think of is running through this again, I guess. So let's try to do that. Maybe there's some mistakes somewhere. All right, so let's see. So we've got our libraries. It's not an issue. And then the accuracy should be correct. Am I true? Yeah. Okay, then we create the data, make blobs, 150 samples, difficult to classify. Then we do the train test split. That's pretty standard. X train X test, Y train Y test. That's correct. We print the data. You can see it here. The values go from negatives to positive. Okay. The labels are zeros and ones. Zeros and ones. Oh, wait a minute. Let me try something. What if I do, if it's a 0, I'm just going to try something. If I greater than 0, I greater than 0, I'm going to make it a positive 1. Else, I'm going to make it a negative 1. So just, changing to this nature where one is a -1 and a +1, right? So I did pretty much, I'm changing the labels now so that they should be in a different range. So instead of 1 and 0, they're negative, -1 and +1. So this, we can actually print the whole array. That should be pretty easy. That's a Y. This. Let's just take a look at it. All right, so let me save on it. you can see I changed the, oh, there you go. There's a little bit of a change. Did you guys see that? So now I changed them from -1 to 1, right? So some are negative, and it gave me 0.5. So still not great, but there was a change. I just changed the labels. So let's try, let's try 1,500 samples. I'm already doing 2,000 iterations. So I don't think. All right, let's just see if we give it more data, if that works. Or if it's still at 50. So let's run. All right, it's trying to do its thing there. So let's wait. This is going to take a little bit longer because it's now, instead of 150 samples, it's 1,500. So taking a little bit longer. But let's see what happens. Oh, there's the answer actually, 0.46 again. So it actually went down. Okay. What else? Got the data. Learning rate 0.1. We could change that, I guess, but number of iterations. I'm going to change this back to 1,000 so it doesn't overfit. All right, let's try this one. Still 46. Wow, just doesn't want to learn. Yeah, I don't see anything. It's possible that if we had initialized the weights to not zeros, but instead to random, maybe that would give better results. I'll play with that. That's a possibility. Because I create the weights as zeros, but I could create this as random values. So let's see, maybe here, note dot product, that's correct, I think. The activation function, that should be correct. The learning rate, correct. And then the updates, let's see, weights is equal to weights plus update times xi. That's correct. Bias is bias plus update, so I don't see anything wrong there. All right, so I'll have to think about it, but you've seen it. Maybe you guys can also think about it, and I'm sure by next Monday we'll have a solution. So let's stop here for today. Okay, so I'll double check this again. We know the algorithm works, but it's just the code works, but the algorithm is not learning basically. So I need to figure out why it's not learning better. could be the data, could be some mistake I made. Could be the weights vector needs to be initialized to a more random distribution. I'll take a look, and then next Monday I'll have a solution. Next Monday we will also start other techniques. Did we talk about a second exam, guys?
I don't think we did.
Right. So we need to have a second exam. Okay. So obviously it won't be next week, but just pay attention that probably in about 2 weeks we will have a second exam, right? Just similar to the first one, some written exam. All right. All right. Okay. So that's basically it for today. Let's. I'm going to